What would you do if you woke up, checked your phone and saw a serious headline saying scientists have just found a way to travel 10 times faster than light? We're going to unpack how that could even be possible without breaking Einstein's rules, what's really happening inside those strange new lab experiments that claim to sculpt space-time itself. To feel why 10 times light speed matters, you need to remember what the speed of light actually is. In empty space, light moves at about 300,000 kilometers per second. That number is not just how fast light is, it's baked into the structure of reality and shows up in how time, space, mass and energy all relate. Now scale that by 10. At that effective rate, Earth to the Moon, about 380,000 kilometers, becomes a blink. You don't spend days in transit, you barely have time to check a message. The math is simple, distance divided by speed, but the answer is so small that your gut wants to reject it. Because every rocket launch you've ever watched has trained you to think of space as slow and painful. So what does that speed actually do to your future? Start with Mars. Today, a human trip takes many months, plus picky launch windows when the planets line up just right, an effective 10 times light warp speed, that close approach distance collapses to minutes, bad alignment trips to maybe hours. Mars shifts from huge one-way gamble to mission you can go on and actually come back from on a normal timeline. Push the thought farther out. Jupiter, Saturn, their moons right now are years away for robotic probes. With a working warp bubble, those worlds move into the weeks, not years category, with crews and schedules instead of once per decade shots. The solar system changes from a place you visit rarely to a network you can actually use. Then your eyes go to the stars. Proxima Centauri, a bit over 4 light years away, is currently so distant that our best chemical rockets would need tens of thousands of years to get there. At 10 times light speed, you're talking about a few months on board, still extreme but no longer absurd. Exoplanet lists turn from background trivia into a menu of reachable systems. But here's the problem, and it's huge. Isn't this exactly what Einstein said you cannot do? You were taught that nothing with mass can reach the speed of light. As you push an object faster and faster, its resistance to acceleration effectively increases. Each bit of extra speed costs more energy than the last, and when you do the relativistic math, you find that as your speed approaches light speed, the energy you need to get any closer blows up without limit. Without limit is not just dramatic wording. It means there is no finite pile of fuel, no clever engine that lets you hit light speed by simply pushing harder through normal space. This is not an engineering problem, it's a geometric one. And we don't just trust the theory blindly, we've tested it. In particle accelerators, we pump huge amounts of energy into protons, and they don't leap to 10 times light speed. They crawl closer to light speed while their energy spikes. So how can any serious scientist now use the phrase 10 times light speed and keep their credibility? The trick is that they're not claiming to shove a ship through space faster than light. They're claiming to move space itself. That's the core of Miguel Alcubierre's idea from the 1990s. A warp bubble of almost flat space carrying a ship, while space-time is compressed in front of the bubble and stretched behind it. Inside that bubble, you and your ship float. Locally, you never move faster than light relative to the space around you, so you never break the speed limit in the usual sense. But the bubble itself, as a region of space-time, can slide relative to distant stars as fast as you like, because the rules about the speed limit apply to objects moving through space, not to the expansion or contraction of space itself. Cosmology already uses this to explain how, in the early universe, regions of space separated faster than light without breaking any laws. That's the loophole this new prototype leans on. The researchers are not saying Einstein was wrong, they're saying we're using Einstein's theory in a very aggressive configuration. On paper, they solve the same equations we use for black holes and cosmic expansion, but with a specific energy pattern around a ring. That pattern, in theory, creates a tiny warp-like bubble in the center, a mini version of the Alcubierre spacetime. So what does that look like in a lab, not in a movie? The device that triggered your notification is not a sleek ship, It's a ring or stack of rings, a few centimeters across, sitting on an isolated table. It's cooled, shielded from vibrations, wrapped in lasers and detectors. When they drive current through it in a very specific way, the energy density around the ring should change just enough to nudge the space-time inside. To test whether anything real is happening, they send laser beams through and around that inner region and measure how long the light takes and how the beams interfere when they recombine. If space-time inside the ring is even slightly distorted, light that goes through the bubble path will arrive a little earlier or a little later than light that takes a reference path. The differences are tiny, measured in billionths or trillionths of a second, but modern interferometers are built exactly to see changes that small. According to their data, the timing shifts and interference patterns they record match, within experimental error, the predictions for a very small Alcubierre-like warp configuration. The effect is microscopic. You couldn't ride this bubble. The effective speed advantage it represents is useless for travel, but it matters because it shows that space-time can be shaped on demand into a form we used to treat as pure theory. And that drops you at the edge of a harder, more disturbing question. If we can already make a tiny lab-scale warp effect, does that mean faster-than-light travel is now just a brutal engineering project, or is there some deeper law, maybe tied to causality or quantum gravity, that will bash or smash these bubbles as soon as we try to scale them up? To see how real that threat is, you need to look at why the light speed limit was treated as unbreakable in the first place. So if scientists now claim a warp bubble can beat light, how can that be true in a universe that has spent a century enforcing a speed limit? To see how shocking this claim really is, you need to understand why physicists were so confident that faster-than-light travel was not just hard but off the table. Start with one number, the speed of light in vacuum, roughly 300,000 kilometers every second. That sounds like just a fast thing, the way sound has a speed in air, but in relativity this number is way more than that. It's the built-in conversion rate between space and time themselves. If you measure distance in light seconds, then moving 1 light second in space is as fundamental as moving 1 second in time. The same constant shows up in how electric and magnetic fields interact, in the relation between mass and energy, and in the way gravity propagates. When Einstein wrote down his equations, this speed fell out as a structural property of space-time, not a detail you can tweak. You see it in technology too. GPS satellites orbit high above Earth, moving fast and sitting in weaker gravity. Both effects make their onboard clocks tick at a slightly different rate from the clocks on the ground. If engineers ignored relativity, GPS positions would drift by kilometers every day. The corrections they apply are calculated using this same light speed constant. So when you talk about breaking the speed of light, you're not just talking about making a faster vehicle, you're talking about messing with the calibration of reality itself. That raises an obvious question. What happens to you, to your time, as you start to push close to that limit? Here's where things get counterintuitive. As your speed approaches light speed, your time slows down compared to someone who stays at rest. Imagine you on a ship and your friend stays on Earth. At 90% of light speed, your onboard clocks tick more than twice as slowly as theirs. For every year that passes for you, more than 2 years pass for them. Push your speed to over 99% of light speed, and the gap gets extreme. Your trip can feel short while decades pass back home. This isn't theory floating in a vacuum, we've measured it. Unstable particles called muons, created in the upper atmosphere by cosmic rays, should decay before they ever reach the ground if you use non-relativistic physics. But they're moving so close to light speed that their internal clocks run slow, they live long enough in our frame to hit detectors at the surface. In particle accelerators, we see the same effect under controlled conditions. And in everyday hardware, atomic clocks flown on fast airplanes, or perched on satellites, tick at slightly different rates than identical clocks on the ground, exactly as relativity predicts. So if time itself stretches for you as you go fast, what does that do to the energy bill for trying to reach light speed? The answer is brutal. As you get closer to light speed, your resistance to acceleration increases. In simple Newtonian physics, you add the same chunk of speed every time you apply the same push. In relativity, that pattern breaks. Each new push still gives you more energy, but less extra speed than the previous one. As your velocity creeps toward light speed, the amount of energy it takes to get a tiny bit closer rises sharply. When you write it out in the relativistic formulas, you find that the energy needed to actually hit light speed would be infinite. Again, this isn't just in textbooks. Big accelerators like the Large Hadron Collider pour staggering amounts of energy into protons. The proton speeds go from 99.9% of light speed to even more nines, but they never cross the line. Almost all the extra energy shows up as increased relativistic mass, meaning more and more inertia, while the speed stubbornly stays below light speed. So for anything with mass, rockets, bullets, starships, you can't just floor the throttle and hope to smash through. The universe doesn't let you. But then why do you sometimes hear that things can move faster than light? This is where language gets tricky. You might hear that particles can go faster than light in water or glass, and that's true, but it doesn't mean they're breaking the real limit. In a material like glass, light is slowed down because it interacts with the atoms in that material. The speed of light in glass is lower than the speed of light in a vacuum. A charged particle can move through that material faster than light moves through that same material while still moving slower than light would move in empty space. When that happens, the particle emits a shock wave of light, a cone of blue glow called Cherenkov radiation. Nuclear reactors in water pools show this eerie blue light, not because anything is violating relativity, but because some particles are outrunning the local light speed in that medium. The key point is that the true universal limit is the speed of light in vacuum. Nothing with mass has ever been seen to outrun that anywhere. So if the equations say no and the lab tricks don't really cheat, what about nature's biggest, longest baseline experiments? The universe has been running tests for billions of years. In 1987, a star in a nearby galaxy exploded as a supernova. Detectors on Earth picked up a burst of neutrinos, tiny, almost massless particles, followed by the light from the explosion, after both had travelled about 168,000 light-years. The arrival times matched what you expect if both signals move at basically the same speed, with neutrinos just a hair under light speed. No sign of neutrinos blowing past light and arriving years early. More recently, observatories detected gravitational waves from colliding neutron stars, ripples in space-time itself, and almost at the same time, telescopes caught the flash of light and gamma rays from the same event. These signals travelled over 100 million light-years and still arrived within seconds of each other. That puts an incredibly tight limit on any difference between the speed of gravity, the speed of light, and the speed of the particles carrying the information. If anything were routinely beating light speed in vacuum, you'd expect big mismatches in arrival times. We don't see them. So nature, on scales from subatomic particles to exploding stars, keeps confirming the same message. Light speed in vacuum is the ultimate speed for information and for anything with mass moving through normal space. That's why the idea of faster than light travel has always sounded like fantasy, not because physicists lack imagination, but because every experiment and every observation keeps pointing in the same direction, which is exactly what makes this tiny, lab-scale warp result so disturbing, because if that holds up, then it's not denying the speed limit, it's trying to slide sideways around it. And that raises the next sharper question: if you can't outrun light by moving through space, can you still win by reshaping space itself? And what kind of physics hack does it take to even write that down without breaking everything? How do you get from nothing outruns light to a serious physicist calmly publishing a blueprint for a warp drive? That started in the mid-1990s, when Miguel Alcubierre, a young researcher who liked Star Trek, asked a question most people would only ask as a joke. Does Einstein's own theory secretly allow something like a warp drive if you push the math hard enough? Instead of writing, he opened a notebook, took general relativity, and went hunting for a very specific kind of solution. The target was clear. He wanted a way to arrange space-time so that a region of perfectly normal flat space could move from point A to point B. Inside that region, a ship would just float in freefall, no engines, no thrust, no local violation of the speed of light. But when you look from far away, from the point of view of distant stars, that whole bubble of space could move faster than a beam of light leaving at the same time. That sounds like cheating, but it's technically not. Alcubierre wasn't asking, can the ship go faster than light through space? He was asking, can I shape space itself so that a chunk of it moves however I want? When he solved Einstein's equations with this goal in mind, he found a specific geometry that did exactly that. Space is almost flat inside the bubble, strongly distorted in a thin shell around it, and normal again outside. The ship never breaks the local speed limit. Yet the bubble's effective speed, as seen from far away, can be anything. So what does this bubble actually do? You compress space in front of the bubble, stretch space behind it, and keep your ship sitting in the calm center. Space in front is constantly being brought closer, space behind is constantly being pulled away, and your pocket of flat space rides along as the geometry updates. From your point of view on board, you're just coasting. From outside, your starting point and destination are being shoved toward each other by shifting space-time. This is the key trick. You never move through the space next to you faster than light. Locally, light still outruns anything you do, but if you compare your motion to some star light years away, the effective speed of your bubble can beat a light beam that left at the same time. That's why physicists say the warp drive doesn't technically break relativity, it exploits it. It uses the same machinery that lets the universe expand faster than light on huge scales and tries to pack that behavior into a controlled bubble. On paper, it works well enough that the math doesn't immediately scream impossible. So why didn't we instantly start designing starships in the 90s? Because as soon as people calculated what kind of energy this bubble would need, the idea hit a wall. The first big problem was the sheer amount of energy required. Early estimates plugged Alcubierre's geometry into the equations that relate curvature and energy, and the numbers that came out were ridiculous. You didn't just need a lot of power, you needed something like converting whole stars into the stuff that shapes the bubble, all concentrated in a thin shell around the ship. That's so far beyond any realistic technology that it might as well be magic. If those numbers were final, Alcubierre's drive would be a math curiosity and nothing more, sitting next to wormholes as things the equations allow but nature will never let you use. Then there was a second, stranger requirement. The bubble doesn't just need a lot of energy, it needs the wrong kind of energy. In most situations, the energy density of space is non-negative. You can add mass, radiation, pressure, but the total doesn't drop below the baseline vacuum. The warp bubble flips that. It demands regions where the energy density is effectively negative, where the vacuum has less energy than empty space. At first glance, that sounds impossible. But quantum field theory already hints that the vacuum isn't a flat zero. Even in empty space, fields fluctuate. The Casimir effect shows this. Put two uncharged metal plates extremely close together, and some quantum fluctuations are suppressed between them compared to outside. That change in the vacuum energy produces a tiny attractive force drawing the plates together. We've measured that in the lab. That means negative energy, in a limited sense, is not pure fantasy. You can create a region where the energy density is lower than the surrounding vacuum, as long as you pay for it somewhere else. Quantum inequalities suggest you can't have large amounts of negative energy for long periods over big regions, but the door isn't completely closed. For warp ideas, that small experimental crack is enough to keep the concept alive. Once that was clear, people went back to Alcubierre's original design and asked a practical question. Are we stuck with this exact bubble shape, or can we redesign it to be less insane? The original warp bubble was simple and symmetric, good for a first paper, but terrible for energy efficiency. Later work tinkered with the bubble's profile, changing how sharply space is curved in different regions, redistributing where the negative and positive energy sits. As those designs got more sophisticated, the required total energy started dropping. not to something you could plug into a wall socket, but from all the energy in the universe down to still absurd but many orders of magnitude less absurd than before. Some models took it from galaxy scale down toward what you'd get from a large star, or even less if you accept lower effective speeds. None of these upgrades suddenly made warp drives easy. We're still talking about energy scales way beyond our reach and about negative energy in amounts we have no idea how to produce or control. But the fact that the numbers were flexible at all was important. It meant warp drive wasn't a one-shot curiosity where the first calculation kills it forever. It became a design space, something you could optimize and in principle try to connect to real experiments. And that brings you back to the present, where a lab claims to have built a tiny device that imitates one of these optimized warp metrics on a microscopic scale. If the original theory went from cute but useless to maybe, just maybe with smarter geometry, then the next step is obvious. Stop arguing on paper and test whether space-time actually responds to these patterns of energy the way the equations predict. Which raises the next question with a lot more tension behind it. When you shrink a warp bubble down to the size of your hand, surround it with lasers and watch how light moves, do you really see space-time bending on command? Or are you just staring at noise and wishful thinking dressed up as data? So what does a warp experiment actually look like when it's not a starship but a piece of hardware you could, in theory, carry with two hands? In the lab, it's not glamorous. It's a ring about the size of a dinner plate sitting on a fat, heavy, vibration-isolated table. Cables everywhere, lasers on optical rails, mirrors, vacuum chambers, cryogenic lines, racks of electronics humming into the background. If you didn't know what you were looking at, you'd think it was just another optics experiment. The claim is very specific. The team says they can drive currents and fields around that ring in such a way that the energy density in the space near its center matches, in miniature, the pattern from a warp metric. Not a full Alcubierre bubble, but something with the same basic structure, positive energy here, negative like effective energy there, arranged to nudge space-time in a controlled way. The warp region they talk about is smaller than your hand, but for the first time the words warp and apparatus share the same physical table. You're not supposed to take that on faith though. You need a way to ask space-time itself if it's been pushed. So how do you actually measure a dent in something you can't see or touch? The answer is you ask light very politely if its path has changed. When they power up the device, they send ultra-stable laser beams through the central region and around it, splitting and recombining them in different paths. In perfectly flat space with nothing changing, those beams should interfere in a fixed pattern, bright and dark bands that stay put, and their arrival times at the detectors should be locked in. If space-time inside the ring is even slightly curved, those paths change by tiny amounts. One beam may have to travel just a bit longer in space-time than the other, even if the physical distance looks the same on a ruler. That shows up as a shift in the interference pattern. The bright and dark bands slide by a small fraction of a wavelength, or as an arrival time difference, measured in trillionths of a second. The instruments in this kind of lab exist for exactly this job. They can see distance changes smaller than the size of an atom. So the experiment runs in cycles, fields off, measure the baseline, fields on, measure again, repeat hundreds or thousands of times. They average out noise from temperature changes, building vibrations, electronic drift. If a consistent difference appears only when the warp configuration is active, and that difference matches the predicted signature from the warp metric they are trying to simulate, that's the beginning of a case that something real is happening. But that raises another question. How do you know that the signature you're seeing is really space-time curvature, and not just your hardware misbehaving? Here, the team leans on tools astronomers have used for decades: gravitational lensing. In space, massive objects like galaxies and clusters bend the paths of light from background galaxies. The result is distorted shapes, stretched arcs, sometimes even full rings. By measuring exactly how those images are warped, astronomers infer where the mass is, even when that mass is dark matter that doesn't emit light. The Warp Lab borrows that logic, just on a tiny scale. Instead of galaxies, they have the engineered energy distribution around the ring. Instead of distant galaxies, they have laser beams and interference fringes. They build models that say, if the space-time curvature looks like this, the light patterns should change in this exact way. Then they check if the real data matches those models better than it matches any boring explanation, like heating, mechanical flexing, or electromagnetic interference. When they map the small shifts in their interference patterns onto an effective curvature in the lab region, they're doing a mini version of how we map dark matter in clusters. Same math, different setting. If that mapping holds up under scrutiny, it means they're not just claiming curvature, they're measuring it with established techniques. That still leaves an important doubt though. Are we really bending space-time, or are we just building a system that behaves like space-time on paper? Physicists already have a whole field called analog gravity, where they build systems that obey the same equations as curved space-time, even though they're made of totally different stuff. In a Bose-Einstein condensate, a cloud of atoms cooled to almost absolute zero, sound waves can behave like light near a black hole horizon. In flowing fluids, you can create a region where disturbances can't escape upstream, mimicking an event horizon. These setups have even produced radiation that looks like the predicted Hawking radiation. Not from a real black hole, but from the analog system. Warp experiments might sit partly in that category. When they tune fields around the ring, they may be building an effective metric, a system where light in the lab obeys equations that look like light moving through warped space-time, even if the underlying cause is a complex refractive index or some engineered medium. From the point of view of the math, that still matters, because it tells you that the geometry you want is, at least in principle, physically realizable. But if the latest claims are right, they go one step further. They argue that in their setup, the effect can't be explained away just as light moving through a weird material. They're saying we've accounted for all known optical effects, and there's a residual that matches genuine metric curvature, a real change in space-time distance. That's a much stronger statement, and it's exactly why other groups are going to try to replicate it and tear it apart. Even if you accept that the effect is real, there's a final nasty hurdle: scaling. How does the energy cost grow as you try to make the warp region bigger or stronger? When they plot amount of energy or field strength versus size of the effective bubble, the line climbs very quickly. Double the linear size, and the required energy jumps by much more than a factor of 2. Increase the desired effective speed, and the requirements grow even faster. That's the brutal reality check. The math still punishes you as you aim for anything useful. But here's where the experimenters get stubbornly optimistic. In the very first warp designs, the scaling was essentially hopeless. Energy went up almost like the bubble size to some huge power. With smarter geometries, that curve bends down, not into something easy, but into something that at least changes when you work on it. Each redesign of the ring, each better field configuration, shaves off orders of magnitude in the theoretical requirements. So the plot on the whiteboard still looks like a mountain, steep and dangerous. Going from a bubble the size of your hand to one the size of a room or a ship is nowhere near our capabilities. But it's no longer an infinite cliff that says don't even try. It's a very long, very hard climb, with the first meter or two now carved into the rock by these tiny lab rigs. And that leads straight into the next question you should be worried about. If you ever did manage to sit inside one of these bubbles, riding it at 10 times light speed, what would that actually feel like? And what new problems would appear the moment you stop treating warp as a lab toy and start treating it as a vehicle? How do you wrap your head around sitting completely still while your entire world is moving faster than light? Inside a perfect warp bubble, that's exactly your situation. You're not being pushed, you're not being thrown, you're just floating in a region of calm, almost flat space-time. The crazy part, the distortion, is all outside you, in the shell of the bubble itself. The bubble compresses space in front, stretches it behind, and your little pocket in the middle just comes along for the ride. Because of that, you don't feel thrust. There is no rocket burn, no shaking, no violent acceleration, no G-forces pinning you to your chair. Your inner ear stays boringly normal. You could literally be playing cards, sipping coffee, while relative to some star system ahead of you, your bubble is covering distance at 10 times the speed of light. From your point of view, it feels closer to being parked in a room while the building slides under you at impossible speed. And that leads to an uncomfortable question. If you feel nothing, but the outside world sees you doing something outrageous, what happens to your sense of time compared to everyone else's? In a classic near-light-speed rocket, time dilation becomes a big deal. Your clocks slow down compared to clocks back home. With an ideal warp bubble, inside your pocket of space, time can be made almost normal. Your clocks tick at their usual rate. Your body ages the way it would on Earth. You experience the trip as a straightforward amount of time, weeks, months, whatever your mission plan says. But to an outside observer, what your world line, your path through space-time is doing is strange. There are trajectories where you leave Earth, a light beam leaves at the same instant, and you arrive at a distant star system before that light does. You didn't feel anything special, but in the global picture, you've beaten a signal that was supposed to be unbeatable. That's where theorists start to get nervous, because it brushes right up against causality, the rule that causes come before effects in every frame of reference. Once you have even one way to do this, clever setups can chain multiple warp trips together, or combine them with other relativistic tricks, to build scenarios where signals seem to arrive before they're sent, at least from some points of view. On your ship, time felt fine. On paper, in the diagrams, alarms start flashing. So if your clocks feel normal but your path looks like a cheat, what does the outside universe look like to you while all this is happening? When you look out the window of a warp ship, you are not seeing a calm, familiar sky. Simulation suggests the view could be seriously disturbing. Light from ahead of you gets piled up into a smaller and smaller patch of sky as the bubble's geometry drags more incoming light into a tight cone. That light can be shifted to higher energies, pushed toward the blue, ultraviolet, even X-rays or worse. Behind you, the opposite happens. Everything stretches out, reddens and fades as light is dragged away. We already see related effects in nature. Jets from active galaxies, where matter screams out at relativistic speeds, show beaming and brightening in the direction of motion. One side of the jet looks brighter and bluer than the other because of these relativistic boosts. A warp bubble exaggerates and reshapes those same basic effects. The forward sky might become a glaring, dangerous spot, not a set of calm stairs. So now you hit the next nasty issue. If the light in front of you is being squeezed and boosted like that, what about all the other stuff in your way? Dust, gas, stray particles spread through interstellar space. Even empty space isn't empty. There's about 1 proton per cubic centimetre on average, plus dust grains, photons, and the odd larger bit of junk. As your warp bubble moves, it doesn't politely pass through all that. It tends to gather it, like a snowplow pushing snow. The geometry of the bubble funnels particles and radiation toward the front. Over long distances, that adds up to a compressed, energetic mess sitting on the leading edge of your space-time pocket. At some point, you have to slow down, you have to turn off or at least reshape the bubble. When you do that, the energy and particles that have been crammed into that forward region have to go somewhere. If you're not very careful, you risk releasing a burst of high-energy radiation and particles into the space in front of you. If that in front of you happens to contain a planet, a station, or another ship, you've just turned your arrival into an attack, even if you didn't mean to. That's why people talk about warp as an accidental weapon. A drive that can move you between stars could, mishandled, also fry surfaces with intense bursts of radiation. So you get another control problem, not just how do I go fast, but how do I turn this thing on and off without blasting my destination? And that leads right into a deeper headache. Even if you know where you want to go, can you actually steer this bubble from the inside? The original Alcubierre setup has a very awkward feature. The front edge of the bubble, the part that actually interacts with the space you're moving into, can be causally disconnected from the interior. In simple language, signals you send from inside the ship can't easily reach the front wall of the bubble to change it. That means you can't just grab a joystick and turn left. The geometry that defines your path has to be encoded in the bubble from the moment you create it. Practically, that means your navigation is mostly pre-planned. You calculate the bubble, you program in the trajectory, you fire it up, and then you ride it. If something unexpected appears ahead, an asteroid, debris, another ship, you may not be able to tweak your path in time or at all. That's a nightmare from an engineering and safety perspective. It pushes you toward extremely conservative routes, huge safety margins, and massive amounts of pre-computed data about the space you're crossing. Later theoretical work tries to fix this by designing warp metrics that restore some control from the inside, but every fix has trade-offs. More control can mean more energy, more complexity, or new instabilities. You're basically asking space-time to be both your engine and your steering system, while also obeying brutal rules about information flow. So here's the tension point. From your seat on the ship, warp feels calm, almost boring. No thrust, no time weirdness that you can feel, just a long trip inside a floating room. But the more you look at the global picture, the more dangerous it gets for causality, for anything in front of you, and for your ability to steer and stop safely. And we haven't even hit the worst part yet, because once you admit that something can effectively outrun light, you bump straight into the question physics hates the most. Does that mean real-time travel? And if so, why doesn't the universe tear itself apart with paradoxes? How do you keep cause and effect in the right order when you've just built a machine that can beat the thing that's supposed to set that order? Relativity has a very clear opinion on this, and it's not comforting. In this theory, what counts as at the same time is not universal, depends on how you're moving. Two events that look simultaneous to you might happen in a different order for someone flying past at high speed. As long as nothing goes faster than light, everyone still agrees on what can influence what. But the moment you allow any signal, any ship, any bubble to outrun light, you can draw space-time diagrams where a message leaves one place and arrives somewhere else before it was sent, at least from some observer's point of view. That's a closed time loop. You send a signal, it gets there, someone reacts, sends another one back along a different faster-than-light route, and in your frame the reply pops into your inbox before you ever hit send on the first message. You can push it further, put a bomb, a warning, or a warp ship itself in that loop, and suddenly you're in grandfather paradox territory, situations where your own actions in the future can block the cause that created them. Physics does not like that kind of story because it breaks basic ideas of consistency. So why did physicists even play with faster-than-light stuff in the first place? For a long time they used imaginary particles as a safe playground. These hypothetical things are called tachyons, particles that always move faster than light. They don't exist in our current models, but they're very useful as a thought experiment. You imagine two observers moving relative to each other, trading tachyon signals. Each one sends a message that in their own frame moves forward in time. When you transform between frames using the rules of relativity, you find at least one frame where the reply arrives before the original message was sent. That's the key lesson. The combination of relative simultaneity and faster than light almost automatically builds paths that loop back in time. You don't need exotic setups, just multiple observers and the ability to route FTL signals in different directions. Decades of searching in accelerators and cosmic rays haven't found any real tachyons. That failure's not a proof, but it fits the pattern. The universe seems very hostile to anything that would casually let you send information backwards in time. Now plug warp bubbles into that picture. On their own, a single simple warp trip might be okay. The ship leaves point A, arrives at point B faster than a light beam, but in a way that, when you draw the full spacetime geometry, doesn't quite make a loop. But as soon as people started analysing these metrics in detail, they realised you can do more. If you chain multiple warp journeys together, or mix a warp bubble path with other curved spacetime structures, like wormholes or certain rotating mass setups, you can create closed time-like curves pathed through spacetime that bring an object back to its own past. That's not just sci-fi hand-waving, it comes out of the same equations that give you black holes and gravitational waves. Some configurations of bubbles and trajectories turn spacetime into a loop machine. That suggests a nasty possibility. Maybe nature quietly forbids those configurations. Maybe the same quantum gravity effects that smooth out singularities or prevent some exotic geometries also explode or destabilize any warp setup that tries to become a time machine. We don't have a full quantum gravity theory yet, so right now this is a huge question mark sitting on top of every warp idea. If closed time loops are easy to build once you have strong spacetime engineering, why don't we see any sign of them in the sky? That's the next thing to check, and the answer so far is nothing obvious. When we look at the cosmos, we see supernovae, gamma-ray bursts, black hole mergers, all following rules we can model without timeline violations. We don't see particles arriving with impossible energy histories, or signals that clearly encode information from the future. The cosmic microwave background, the leftover radiation from the early universe, is smooth with tiny random ripples. Its pattern looks exactly like what you expect from a universe that evolved forward in a pretty boring way, not one that's been heavily edited by time travelers bouncing around the early cosmos. Again, this is not a rigorous proof. Maybe time games are rare or carefully hidden, but the data so far leans toward a universe that protects causality, at least on large scales, and that should make you nervous if you're trying to sell a warp drive as a simple transportation upgrade. So where does that leave a real prototype, the kind of device this video is pretending just got announced? If the people behind it are honest, they're not saying we broke causality, deal with it, they bury a lot of fine print. The effective 10 times light speed might only be true in a very specific frame of reference, like the lab frame. The bubble might only exist for very short times and over very short distances, not long enough to string together into a loop. The geometry might be constrained so that if you draw the full spacetime diagram, there is no way to arrange multiple uses of it into a closed causal path. In practice, the research team's data release would come with a stack of plots, world lines, and causal structure diagrams. They'd show like cones, those regions of spacetime that can be influenced by events, and they'd argue that, within the range and accuracy of their experiment, all cause and effect chains still run forward. They'd say something like, yes, we have an effective FTL behavior here, but no, you cannot chain it with any reasonable motion to send a message to your own past. Not with this configuration, not at this scale. That is the tightrope any serious warp experiment has to walk. Powerful enough to show a real effect, limited enough that you don't immediately unleash paradoxes. The tension is obvious. Every improvement that makes the warp bubble more useful also nudges it closer to the dangerous zone where closed loops might appear. Somewhere in that space, quantum gravity, energy conditions, or outright instability may slam the door. But we don't know where that line is yet. And that pushes you straight into the next brutal question. Even if nature allows these bubbles without breaking time, can you actually feed them the kind of energy they need? When their shopping list looks less like big rocket fuel tank and more like, you got a spare star lying around? How much raw power do you actually need to bend space-time on purpose, not as a metaphor, but as a machine spec? Start with something you already think is huge, a Saturn V rocket. When that thing launched, it turned its fuel into exhaust with a total energy release of roughly 100 trillion joules. That's enough to throw humans at the moon. Sounds massive until you compare it to the kind of numbers that show up in warp drive papers. Take 1 kilogram of matter and 1 kilogram of antimatter, let them annihilate each other completely, and you get close to 100 million trillion joules. That is an insane number by everyday standards, and even that is still small compared to some of the early warp concepts, which casually asked for energy on the scale of what the sun puts out over years just to make one bubble big enough to fit a ship. So line it up. A moon rocket gives you 100 trillion joules, a full matter-antimatter burn gives you around 100 million trillion, and some warp designs laugh at both and say, nice toys, but we need more. That's why serious physicists used to treat warp drive energy budgets as a punchline. You're not arguing about engine efficiency, you're arguing about access to star-level resources. Which leads right to the next uncomfortable comparison. What can stars and black holes do that we absolutely cannot? Look at the sun. Every second, It's putting out something like 400 billion joules of power. That's its continuous output, just sitting there doing nuclear fusion. Now look at accretion disks around spinning black holes. As matter spirals in, friction and magnetic fields can convert a big chunk of that mass directly into radiation. Some quasars shine brighter than entire galaxies, all because a black hole and its disk are terrifyingly efficient engines. Warp engineers, at least on paper, are basically staring at those monsters and saying, we want to imitate a tiny fraction of that power density in a controlled ring without blowing ourselves up. They want field strengths and energy densities that in nature only show up in the most violent places in the universe, but they want them in a lab with good safety protocols and a user manual. That's the scale mismatch we're talking about. So where could such extreme energy even come from if you're not literally building a star in your engine room? This is where people start pointing at exotic energy sources that already show up in physics. Dark energy, for example, seems to give empty space a small but non-zero energy density, and it drives the accelerating expansion of the universe. Per cubic meter, it's tiny, but there are a lot of cubic meters in the cosmos, and the total effect is huge. Closer to home, the vacuum is not perfectly empty either. Quantum fields fluctuate even in what we call empty space. The Casimir effect is a direct sign of this. Put two metal plates very close together, and some vacuum fluctuations between them get suppressed compared to outside. That difference creates a tiny force pulling the plates together. You've effectively changed the energy content of the vacuum between the plates. These effects are small but real and measured. Warp ideas are basically saying, we want to take that ability to tweak vacuum energy and crank it from a tiny lab curiosity up to a mything that can shape space-time on command. You're trying to turn a whisper into a scream without. Breaking the underlying theory. It's a huge leap, but it's not starting from zero. The universe already shows you that vacuum energy is adjustable, at least a little. Here's where we have to come back down to Earth for a second, because today's warp prototypes are nowhere near star level. In the near term, you're talking about energy in the range of millijoules to joules. That's the kind of energy you store in a small spring or a stretched rubber band, not in a fusion reactor. The trick isn't the amount, it's the pattern. If you can arrange even tiny amounts of energy into the specific configuration that matches a warp metric, and then detect the tiny space-time distortion that results, you've already shifted warp drive out of pure fiction into experimental physics. You're not jumping to Proxima Centauri, but you are proving that space-time responds in the direction the theory predicts. That's exactly what the dinner plate-sized rigs are trying to do. This game then becomes all about efficiency. For every design, you can ask, how much warp effect do I get per unit of energy? Can I get the same effective curvature with less total energy? Or can I use smarter field arrangements to recycle or localize what I put in? Theory teams tweak the geometry, chasing configurations where the negative energy regions are smaller, sharper, and demand less overall cost. Experimental teams build hardware that can actually approximate those shapes. It's a loop. Cosmology tells us how space-time reacts to big natural energy distributions. High-field lab experiments show what's possible with magnets, lasers, and materials at their limits. Quantum experiments with the vacuum tell us how far we can push negative energy tricks without the math going off the rails. All of that feeds into updated warp models, which then push back on the engineering, which exposes new limits, which then feeds back into theory again. The long-term hope is simple to say and brutal to reach. Drag the required energy for a useful warp bubble down from you need a sun to you need something like a serious power plant, then down further to this is at least in the same galaxy as future human industry. Each order of magnitude you shave off is a big win, but you need many of those wins in a row to get anywhere practical. So right now, we're stuck with this contrast on the whiteboard. Full-scale warp drive still looks like a cosmic glutton, demanding energy on stellar scales. On the lab bench, prototypes are working with the energy budget of a toy, but arranged in patterns that mimic the giant. everything between those two is missing. And that raises a new kind of problem, even if one day you solve the power issue and you can feed a real warp drive. How do you actually aim this thing through a universe that's messy, filled with gravity wells and junk, when your vehicle is literally a moving chunk of space-time? So suppose somehow you solve the energy problem, you've got a working warp ring sitting around a real ship. Now comes a quieter but equally lethal question. How do you actually fly this thing without killing everyone on board or smashing into something you never saw coming? Warp flight is nothing like pointing a nose and hitting the throttle. Your path is not just where the ship goes, it's how you shape space-time around it. Your trajectory is literally encoded in the geometry of the bubble. That means your flight plan is a solution to Einstein's equations, not a line on a map. Before you launch, mission control has to run heavy simulations, solving the full general relativity problem for where you're starting, where you're going, what massive objects lie in between, and how the bubble should evolve over time. In practice, that means a control room full of astrophysicists and numerical relativity specialists, plus software that's been beaten up for years. Every tiny tweak to the warp field shape has to be checked for stability. Small mistakes in the math can blow up into big distortions as you move. On board, your autopilot is not just doing guidance and control, it's running compact versions of those same calculations, making sure the bubble doesn't drift into a configuration that rips itself apart or slides you too close to a gravity well. So then you ask, even if the math behaves, what are you actually ploughing through out there? Interstellar space sounds empty, but it isn't. Between stars, you still have roughly 1 proton per cubic centimetre on average, plus dust grains, and once in a while small rocks or larger debris. At normal spacecraft speeds, we already treat micrometeoroids as serious threats. At orbital velocities, little grains can punch through metal. At effective faster-than-light speeds, even a tiny particle in the wrong place can carry absurd amounts of kinetic energy relative to your frame. Now mix that with the warp bubble picture. As you move, the bubble doesn't politely ignore this material. Depending on the exact geometry, it can push matter and radiation toward the front, or deflect it around you in complicated ways. Any bit of dust you collect at those effective speeds is dangerous. This is why real warp navigation would need pre-cleared corridors wherever possible, routes that avoid dense gas clouds, known debris fields, or regions with lots of small bodies. Your route planning software isn't just drawing a straight line between stars, it's checking catalogues of interstellar medium density, known asteroid populations, and anything else that might turn into a bullet when you arrive. And here's the next kick in the teeth. Your normal sensors are basically crippled at warp. Radar, LiDAR, optical cameras, they all rely on signals that move at or below light speed. If your warp bubble is effectively outrunning any signal you send forward, nothing you emit can get out in front of you, bounce off an obstacle, and return to warn you in time. You have a built-in blind spot in the direction of travel, so you can't see in real time the way a jet or even a normal spaceship can. Instead, you rely on insanely detailed star maps and environment maps built beforehand. Missions like Gaia, which has charted positions and motions of over 1 billion stars with crazy precision, become part of your basic navigation stack. In the future, you'd want similarly detailed surveys of gas, dust, and small bodies. Warp trips start to look like jumping between surveyed nodes, not wandering freely. You might do a series of shorter warp legs, dropping out periodically to scan ahead with normal sensors before spinning up the bubble again. People sometimes suggest throwing probes ahead of the ship, but those probes are still limited by light speed too. They can't report back fast enough while you're in full warp. That's why careful pre-computation and conservative routes become standard. You trade flexibility for safety because the alternative is flying blind through a minefield. And that's before you factor in that space-time itself is not flat and friendly. Real space is lumpy. Stars, planets, stellar remnants, black holes, and even large gas clouds all curve space-time. A warp bubble travelling near one of these masses will feel more than just its own engineered geometry. External curvature will distort the bubble, possibly bending its path, changing its effective speed, or destabilizing it entirely if you get too close. The nice clean warp metric in the textbook assumes a simple background. The real universe does not give you that. We already map these gravity wells using multiple methods: the motions of planets and moons, the timing of pulsars, the way light bends around galaxies and clusters. For warp navigation, all that becomes your terrain data. You'd have three-dimensional space-time maps showing where the curvature is gentle, where it's steep, where there are dangerous gradients you don't want to cross at warp. Staying too close to a massive object while under warp could twist the bubble in ways you didn't plan for, or even trap you in a path that's hard to escape without dumping the drive. So your flight planning software has to look not just at where objects are, but at the full gravitational landscape. It has to choose paths that keep the bubble in regions where its own engineered curvature dominates, and where external wells won't shove you into a weird trajectory. Even things like Lagrange points, where gravitational pulls balance out, become interesting as potential parking zones or boundaries you don't want to cross at speed. Finally, you have to ask the ugly question no one wants to test the hard way. What happens when something goes wrong mid-warp, and you have to abort? With a rocket you can cut thrust. The vehicle will still move, but at least you're not adding more energy. With warp, your engine is a whole space-time structure holding huge amounts of stored energy in its fields. Shutting it down is not as simple as flipping a switch. If you collapse that structure too quickly, you risk dumping that stored energy into your surroundings as a blast of radiation, particles, or violent curvature changes. That's bad news for your ship, and catastrophic for anything near your exit point. We already wrestle with a milder version of this problem in high-field machines. Superconducting magnets in accelerators store enormous energy in their magnetic fields. If a magnet quenches, meaning it suddenly stops being superconducting, that energy can turn into heat fast, damaging equipment. Engineers handle this with carefully designed dump circuits and protection systems that spread the energy out safely. A warp abort system would need the same idea, but scaled up and integrated into the geometry of space-time itself. In practice, a safe abort probably means a multi-stage ramp down. First, you reduce the warp effect gradually, bleeding energy into auxiliary systems or radiation channels pointed into empty space. Maybe you shift to a lower power bubble that still keeps you safe while you slow your effective speed. Only once the stored energy is low enough do you let the bubble fully collapse. And critically, you don't do this anywhere near a planet or station. There would be strict no-warp zones around inhabited systems, and strict rules about where you're allowed to enter and exit warp in the first place. So by the time you've handled navigation, sensing, gravity wells, and emergency stops, you've turned a faster-than-light engine into a huge, tightly coupled ecosystem of maps, simulations, safety corridors, and rules. You're not just building a drive, you're building an entire operating system for moving through a warped universe. And under all of that sits a bigger question: how do we even know where the limits are? What shapes of space-time are allowed, and which ones will blow up in our faces? To answer that, you have to look up and use the universe itself as your instruction manual. How do you design a warp drive when the only working examples we've ever seen are the universe itself? Right now, cosmology is basically your instruction manual because the cosmos has already done things to space-time that look suspiciously like the hacks you want to copy, just on much bigger scales than any engine. Right after the Big Bang, the universe seems to have gone through a phase we call inflation, and this was space-time on overdrive. In a tiny fraction of a second, distances that were microscopic got stretched so fast that regions that used to be in easy communication with each other were yanked far beyond each other's horizons, faster than any light signal could have kept up. We don't see that phase directly, but we see its fingerprints in the cosmic microwave background, the afterglow of the early universe. Temperature is almost the same in every direction, with tiny, carefully measured ripples. The only clean way we know to explain that pattern is to say, space itself expanded at ridiculous faster-than-light effective rates, carrying patches of the universe away from each other. Inflation is basically the universe saying, look, I already know how to do warp. I've done a version of it once, at insane power levels. That tells you two important things. First, faster than light effective motion via spacetime expansion is allowed by the rules. And second, you need the right kind of energy density to drive it, not just a bigger rocket. So then you look around today and ask, is anything still pushing on spacetime like that? The answer is yes, just slower. Right now, some mysterious component we call dark energy is making the expansion of the universe speed up again. We see this in the light from distant supernovae, which are dimmer than they would be in a universe that was just coasting, and in the large-scale structure of galaxies. When we run the numbers, we get a picture where space is stretching faster and faster on the biggest scales. In the very distant regions, galaxies are receding from us faster than light, not because they're flying through space that fast, but because the space in between is growing that fast. So even in the present day, you are living inside a slow-motion warp field, a weak universe-sized version. Dark energy is tiny per cubic meter, but it fills all of space and it's winning over gravity at large distances. For warp engineers, this is both encouraging and annoying. Encouraging because it proves space-time responds in this way to certain energy patterns. Annoying because dark energy is very weak and very global, and you want something strong and local, a drive, not a background drift. That leads to a deeper question, even if you can locally push back on expansion. Are there places you simply can't reach no matter how clever your warp design is? Once dark energy takes over, the universe develops horizons that are not just about distance, but are about forever. There are regions so far away and receding so fast due to expansion that light emitted from them right now will never reach us, not in any finite time. That defines a cosmic event horizon. It's not a wall you can point at, it's a limit in space-time diagrams, a boundary beyond which events can never affect you. Even if you had a warp drive, you'd be fighting the global stretching of space itself. Beyond a certain distance, the expansion wins, and you can't ever fully catch up. Cosmology data from the cosmic microwave background galaxy surveys and supernova observations basically tells you there are regions of space-time that are permanently out of reach of any local technology. That's a harsh cap on what interstellar or even intergalactic travel can mean in the very far future. Warp might let you move around inside your reachable patch much more freely, but it doesn't give you God mode access to the entire universe. So if the cosmos has already done inflation and is currently running on dark energy, how do you turn that from vague inspiration into concrete warp designs? This is where the math becomes your test bench. The same equations of general relativity that we used to model the early universe, black holes and gravitational waves, can be used to explore warp metrics. Researchers plug in different energy layouts, different distributions of positive and negative energy, and then drop test particles into the simulated spacetime to see how they move. Does a bubble form? Does it stay stable? How fast can it move relative to distant observers? Do causal loops appear? It really is like a flight simulator, but the engine underneath is the full machinery of relativity that has already survived a century of tests against real data. When LIGO saw gravitational waves, when we imaged a black hole shadow, those were confirmations that this engine is trustworthy in extreme regimes. Warp designs live or die inside that same math. If you propose an energy pattern that gives you a nice bubble but breaks key energy conditions, or instantly creates time loops, the simulator flags it as unphysical or unstable. Only the designs that pass those checks are even worth thinking about in hardware terms. Once you start thinking this way, you can flip the perspective. Instead of the universe being something that just happens to you, warp concepts let you imagine pushing back against the large-scale flow. Today, distant galaxies are being carried away from us by expansion. In the far future, many will slip over that cosmic horizon and become unreachable. A strong enough local space-time distortion in principle lets you swim against that tide for a while, outrunning how fast your local group is being pulled apart. In theory, you could temporarily reconnect with regions that would otherwise drift away forever, extending the part of the universe your civilization can actually touch. You're no longer just a passenger on the cosmic expansion, you're actively shaping small patches of space-time inside it to your advantage. The expansion history of the universe stops being just background information and turns into a kind of weather report for high-end navigation, something you have to take into account when planning very long-range routes. But knowing that the universe can do these tricks, and that the equations allow scaled-down versions, still leaves you with a brutally practical problem. How do you turn those elegant metrics into actual hardware? Real rings, real fields, real materials that don't melt, fracture, or explode the first time you ask them to hold a warp configuration. When you look at most warp ship designs, real or fictional, they all share one obvious feature, a big ring wrapping around the hull. That's not just for style, that's where the weird energy has to live. The math behind warp metrics usually puts the extreme energy densities in a torus around the ship, not inside it. So in engineering terms, you're probably staring at a massive ring made from advanced superconductors, carrying currents so large they make today's magnets look like toys, all wrapped in heavy magnetic shielding and held at cryogenic temperatures so it doesn't just go normal and die. Inside that ring, the fields are tuned to sculpt space-time. Outside, thick shielding keeps those fields from frying your electronics or your crew. Cooling systems run constantly, moving heat away so the superconductors stay below their critical temperature. Even holding that structure in place is non-trivial. Strong fields push on the ring itself, trying to twist it, expand it, or tear it apart. The iconic warp ring look is basically the visible tip of a huge engineering iceberg, where almost everything important is happening in a few meters of exotic hardware that circles your ship like a halo with an attitude. To actually just shape those fields the way the equations demand, normal materials probably won't be enough. That's where metamaterials come in, stuff we engineer at the micro or nano scale, so that the bulk material has properties nature doesn't hand out for free. We already use metamaterials to bend light in unusual ways, redirecting microwaves around objects, focusing radio waves more tightly than simple lenses can, even making crude cloaking devices in limited frequency ranges. All of this works because we arrange tiny structures smaller than the wavelength of the wave we want to control. Warp hardware might have to do something similar, but one level up in difficulty. Instead of just shaping light, you're trying to shape energy density itself, maybe even how different fields contribute to spacetime curvature. That could mean rings and shells composed of layered metamaterials, carefully patterned to guide electromagnetic fields into strange distributions, concentrating energy in narrow bands while cancelling it elsewhere. Each segment of the ring becomes a piece of a larger pattern, tuned so that when everything is active, the combined effect approximates the warp metric you want. All of that rests on a technology we already use but are nowhere near mastering at warp scales: superconductors. Facilities like the Large Hadron Collider depend on them. Huge superconducting magnets are cooled to just a few degrees above absolute zero, so they can carry gigantic currents with almost no resistance and generate very strong magnetic fields. Even then, we are pushing those magnets near their physical limits. They occasionally quench, which means they suddenly stop being superconducting. When that happens, all the stored magnetic energy starts turning into heat, fast, and you better have protection systems ready, or your hardware gets destroyed. Now, take that problem and crank it up. Warp rings would need fields stronger and more complex than anything we run routinely today, and they'd need to stay stable for long durations, not just for seconds or minutes. The real-world data from places like CERN tells us how ugly things get as we push up against critical field strengths, mechanical stresses, and thermal limits. Engineers would be mining those lessons brutally, using them to define safe zones and red lines for warp hardware. Because when your field collapse isn't just a magnet failure but a warp field failure, the stakes jump from expensive downtime to catastrophic event. To know whether your hardware is doing anything to spacetime at all, you surround it with some of the most sensitive instruments humans have ever built: interferometers. These devices split a laser beam into two paths, send them along different routes, then recombine them. If the paths change by even a tiny amount, the interference pattern of bright and dark fringes shifts. Observatories like LIGO use kilometre-long arms and insanely stable lasers to detect ripples in spacetime from merging black holes. They can see changes in distance smaller than a proton. Your warp lab is a scaled-down version of that mindset. Rings sit inside vacuum chambers, with interferometer arms going through the active region and around it. You run the drive fields on and off over and over, recording how the interference fringes move. Any consistent shift that appears only when the fields are active is a clue. You compare that shift against models for magnetic effects, thermal expansion, mechanical vibrations. Whatever is left over, if it matches the prediction for a tiny warp-like curvature, becomes your evidence that the ring has actually nudged space-time. But making a tabletop rig behave is one thing. Wrapping a full-size starship is something else entirely. Scaling from a ring you can hold with two hands to a structure that encircles a 100-metre-long vessel is an engineering nightmare. Forces that are small in the lab become huge at that scale. Magnetic pressure tries to blow the ring apart. Vibrations move at different frequencies, potentially resonating with the structure and amplifying themselves. Temperature gradients appear along the ring, as some sections absorb more power than others. We already know what happens when you push big machines near their limits. Turbines in power plants experience blade fatigue, cracks, and catastrophic failures over years if you're not careful. Rocket engines tear themselves apart with vibrations if their acoustic modes line up badly. Experimental fusion reactors fight thermal stress and electromagnetic forces constantly. A practical warp ring would combine all of those problems, plus a few new ones, into one device. Structurally, it's like building a skyscraper that has to stay perfectly aligned while being kicked by massive shifting magnetic fields. Electrically, it's like running a particle collider's worth of current through a torus that has to maintain precise field shapes with millimetre accuracy. Thermally, it's like operating a small nuclear plant's cooling system around your hull, because any loss of superconductivity in the wrong place could trigger a cascade failure. When people say warp drive, it sounds like one invention. In reality, it's a stack of mature technologies that barely exist yet, all lashed together around a single goal. And that raises the next problem that's a little less glamorous but absolutely critical. Even if the hardware holds, and the bubble forms and the navigation works, what does all of this do to the human body living inside it? And can we actually keep a crew healthy and sane inside a pocket of space-time being twisted and pushed in ways we've never experienced before? How much can a human body really take when you start bending the thing it lives inside, space-time itself? We already know space is bad for you even before you add warp to the mix. Astronauts on the ISS get several times the radiation dose you get on the ground, even with Earth's magnetic field still helping them a bit. A long trip to Mars in ordinary space already pushes dose levels into a zone where cancer risk and other long-term damage are serious questions, not footnotes. Warp travel adds new radiation problems on top of that stack. At the front of the bubble, you're sweeping up cosmic rays, high-energy particles and stray photons. The bubble geometry can boost their energies and concentrate them. Some of that gets redirected, some of it piles up. Then there are the transitions. When you spin up or spin down the warp field, you can get bursts of high-energy photons and particles, like a snap in the fabric around you. If you do this near a planet, it's a planetary safety issue. If you do it near your own hull, it's a crew survival issue. Shielding becomes a central design problem, not an afterthought. You're mixing everything we've learned from nuclear reactors, particle accelerators, and radiation therapy with the new geometry of a warp bubble. You need layered shields, materials that stop charged particles, materials that soak up neutrons, structures that deflect intense gamma flashes away from crew areas. Maybe you integrate the shielding into the ring itself or into a thick, sacrificial outer hull. Whatever you do, you're budgeting mass just to keep people's DNA from being shredded over multi-month trips at effective superluminal speeds. Then there's gravity inside the bubble. The good news is, in a well-designed warp bubble, you can keep the interior spacetime almost flat. That means you don't automatically get weird tidal forces ripping you apart. Inside that region, you can use familiar tricks for artificial gravity, like rotation. Spin a ring or section of the ship and you get a steady inward pull that feels like weight. Your muscles and bones know what to do with that, it's manageable. But almost flat is not perfect. Any imperfections in the bubble shape show up as tiny gradients in gravity across the cabin. One side of your body might feel a little stronger pull than the other, your head might feel a slightly different feel than your feet. Over seconds, you don't notice. Over months, small imbalances can cause circulation issues, fluid shifts, subtle strain on joints and spine. You're basically living in a dynamic, engineered gravity environment where the physics team and the medical team have to talk constantly. If new warp field configurations change those gradients, you need to know what that does to a human who has to live with it for a long mission. Timekeeping adds another layer of weirdness. In the idealized version, inside the bubble your time passes normally, your clocks tick as usual, and most of the classic relativity time dilation is offloaded to the geometry outside. But real missions won't be perfect. You may do high-speed legs using conventional propulsion to get into or out of warp, or you may park near strong gravitational fields to use them in clever ways. Every one of those phases desynchronizes your clocks from Earth's. We already see small versions of this. GPS satellites, moving fast and sitting higher in Earth's gravity field, have onboard clocks that drift by tens of microseconds per day relative to clocks on the surface. Engineers correct for that constantly. On a warp mission, the offsets could easily be minutes, hours, even days, depending on your path, your gravity assists, and your time in different field configurations. That matters for comms, for coordinating with other ships, and for the basic human question of, how old am I compared to everyone I left behind? You'll need time protocols that treat relativistic offsets as normal, not as edge cases. Psychology is where all of this hits human limits in a different way. We already know long isolation is rough. Antarctic winter crews, submarine deployments, and long ISS missions all show the same patterns: stress, sleep issues, mood problems, interpersonal conflict. Now drop a crew into a warp ship and add a new layer. During a jump, they may be effectively unreachable. No real old-time contact with home, maybe not even delayed messaging, depending on how the bubble and the comms rules are set up. You're not just far away, you're inside a moving pocket of space-time that nothing outside can easily touch while the drive is running. There is no quick rescue, no emergency return, no "we'll get another ship out to you in a week." The crew knows that all the time. That's a different psychological load than anything we've tested. Training has to be tougher, selection has to be stricter, and onboard support has to be overbuilt, with VR, entertainment, counselling systems, and very clear social protocols to keep people functional when the walls are literally space-time and there is nowhere else to go. Finally, medical autonomy stops being a luxury and becomes mandatory. Modern astronauts can talk to flight surgeons on the ground with relatively short delays, send data, get advice. On a warp ship mid-jump, you may not be able to send anything out until you drop back into normal space. That means if someone's appendix bursts, or a bone breaks, or a strange infection appears, you can't just patch them up and wait for expert input. You need real surgical capability on board, not just bandages and a first aid kit. So the ship's medbay has to look more like a compact hospital, with imaging tools, life support, surgical gear, and a lot of automation. Point-of-care diagnostics, small devices that can run blood tests or scan tissues in minutes, become standard. Compact MRI or ultrasound systems get built into walls. Research into bioprinting tissue or rapidly producing custom implants suddenly has a direct use, because resupply is not an option in transit. Crew cross-training matters too. You can't rely on a single doctor. Other crew members need enough medical training to assist in surgery, run diagnostics, and handle emergencies if the primary medic is the one who gets sick. In short, bending spacetime is only half the problem. Keeping a fragile, radiation-sensitive, social, emotional, biological organism alive and sane inside that bent spacetime is the other half. And once you accept that you can do this at all, you hit one more disturbing layer. Any technology that can move ships between stars this fast and store this much energy in a field can also, if misused or mishandled, act like a weapon on a planetary scale. How dangerous is a technology that can drop a starship out of nowhere near your planet? A warp ship isn't just a vehicle, it's a chunk of mass that has been moving with ridiculous effective speed. If it exits warp too close to a world while still carrying a lot of kinetic energy, the numbers get ugly fast. Even at a fraction of light speed, the impact energy is in the range of big nuclear arsenals. Scale it up a bit and you're into the same territory as major asteroid strikes. The rock that helped wipe out the dinosaurs released as much energy as millions of gigaton-class nuclear bombs going off at once. You don't need anything close to that to wreck a civilization. A ship misjumping, exiting warp near the ground, or in low orbit with the wrong residual velocity could cause continent-level damage, trigger tsunamis, or strip atmosphere. That's without even trying to weaponize it. The bare possibility of turning a rival error into mass casualty event drags warp tech straight into the security and arm control conversation, whether anyone likes it or not. Then add radiation to the stack. Remember that snowplow effect at the front of the bubble, where dust, gas and stray photons get pushed and compressed as you move? If you mishandle the shutdown, that stored energy can be dumped into the surrounding space as a concentrated flash of high-energy radiation. Not just a pretty glow, but bursts in X-ray or gamma-ray bands. We already model what nearby supernovae or gamma-ray bursts could do to Earth-like planets. A close, strong enough event can damage the ozone layer, spike surface radiation and drive mass extinctions. A botched warp maneuver could be a scaled-down version of that. Not galaxy-level destruction, but bad enough. You arrive near a world, shut down your bubble the wrong way, and a focused pulse nails its upper atmosphere. Maybe it strips ozone over a large region, maybe it zaps satellites and power grids, maybe it quietly increases long-term cancer rates. You've just carried out what looks from the ground like an attack, even if your crew thought they were just doing a rough test. That's why safe entry corridors far from planets and stations would become non-negotiable. Now think about gravity side effects. Strong warp fields are by definition messing with space-time curvature. Use them near a massive body, and you're not operating against a neutral background. The combined field might nudge local gravitational balances. Even tiny changes in effective gravity over a planet could, in principle, show up as slightly different tides, small shifts in orbits, or stress on the crust. On Earth, we already see measurable crust changes from things like big storms, ice sheets melting, or large reservoirs filling and draining. The planet responds to load changes you'd normally ignore. If warp fields get anywhere close to those scales near a planet, engineers and regulators will freak out correctly. You don't want someone lighting a high-power warp drive in low orbit and discovering it couples to the planet's gravity in some weird way. That's why you end up with strict rules, hard limits on how close to a planet you're allowed to spin up or spin down a serious warp configuration, and careful modelling of any operation in a system with large moons or dense asteroid belts. Of course, rules only work if you can tell when someone is breaking them. In the nuclear age, we built global networks of seismometers, radiation detectors, and satellites to watch for tests. In a warp era, you do the same thing, but for space-time. Interferometer networks and gravitational wave observatories become your new radar. We already have detectors that can feel black holes merging halfway across the universe by measuring tiny changes in distance. It's not a big conceptual step to tune similar instruments to look for the distinctive signatures of artificial warp fields lighting up nearby. A warp-capable civilization would likely maintain a web of such sensors around its inhabited systems. Any large warp event, especially one that violates safe distance rules, would stand out. You'd see the field ramp up, the bubble form, the curvature pattern evolve. That data wouldn't just be for science, it would be for enforcement. If someone tries to run a covert weaponized warp test near a world, the spacetime detectors become your first line of evidence. All of this points at the same conclusion. Once you can bend spacetime on purpose, the laws of war and the idea of safety have to be rewritten. The nuclear age forced humanity to create treaties, inspection regimes, test bans, and shared monitoring, all built on real physics. Warp technology would force a bigger update. You'd need international or interstellar agreements on minimum safe distances for warp jumps, rules about where you can engage a drive, how close. You can exit to a planet and what kinds of bubble configurations are outright banned because they're too easy to weaponize. You'd also need shared detection infrastructure, so no single power can secretly warp in a fleet without everyone else's sensors lighting up. Enforcement would be based on raw data from space-time monitors, not just on trust. And the design of civilian warp drives would be shaped by these rules, with built-in limits on how fast they can transition near inhabited zones, and built-in safety caps on the field strength. At that point, warp stops being just a physics project. It becomes a civilization design problem. How do you give yourself access to the galaxy without giving every angry faction a tool that can casually wreck planets? How do you encourage exploration and trade while making surprise attacks as difficult and obvious as possible? And once you accept that, you run into a bigger, older question that has been nagging us for decades. If warp or anything like it is really possible, why don't we see anyone else using it? And what does that silence say about the survival odds of civilizations that get this far? If warp is even partly real, you have to ask a blunt question. Why isn't the galaxy already obviously occupied? At 10 times light speed, the Milky Way stopped being impossibly huge and starts looking manageable. The disk of our galaxy is about 100,000 light-years across. At an effective 10 times light speed, a ship could cross that in around 10,000 years of ship time, which is long for a crew but trivial for automated probes. Now stretch that out. Even if you move slowly, even if you pause often, even if you only colonize or seed a tiny fraction of systems you pass, a single determined civilization could scatter self-replicating probes or outposts across the entire galaxy in a few million years. That sounds big until you compare it to the age of the galaxy itself, more than 10 billion years. If warp-level travel is workable, then the time scale to fill the galaxy with signs of activity is tiny compared to the time available. So we turn the telescope around and look, and it's quiet. Programs like SETI have listened for decades for narrowband radio beacons, the kind of deliberate, obvious, we're here signal a tech species might send. Infrared surveys have scanned for stars that look suspiciously dim in visible light but bright in heat, as you'd expect from a star wrapped in power-collecting structures. We've catalogued fast radio bursts, pulsars, magnetars, and a zoo of weird phenomena. We've found plenty of mysteries, but none that clearly say, this is a warp empire zipping around and building things. No smooth, galaxy-wide communications grid lighting up the sky. No obvious repeating warp signatures in our gravitational wave data. Just natural astrophysics doing natural things. That silence is the Fermi paradox, amplified by warp if galaxy-crossing speeds are possible. Where is everyone? One possible answer is simple and depressing. The math is kinder than reality. The equations of general relativity allow warp-like solutions, but the true theory, the one that merges quantum mechanics with gravity, might shut them down at useful scales. On paper, you can write a bubble that goes faster than light. In a real quantum vacuum, maybe vacuum fluctuations rip large bubbles apart. Maybe any configuration with enough negative energy density triggers a violent instability, turning your drive into a self-destroying event. In that scenario, small lab-scale effects might exist, tiny warps you can measure with lasers and interferometers, but every attempt to scale them up runs into a brick wall of quantum gravity. Bubbles collapse, fields blow up, or energy conditions that look flexible in classical math snap back into place. So the galaxy stays quiet, not because nobody tried, but because the deep structure of physics blocks anything beyond little tabletop tricks. Another answer is uglier, and it has nothing to do with the equations and everything to do with the species writing them. Warp is not the only extreme technology on the path from early industry to galactic civilization. You pass through stages where you can build self-replicating machines, powerful artificial intelligences, engineered viruses, large-scale climate control systems, and more. Every one of those is a potential self-destruct button. We already see this in our own history. We discovered nuclear physics and almost immediately got nuclear weapons. We changed the planet's climate by accident. We're building machine learning systems that will plug into critical infrastructure. We can edit genomes. None of these are inherently guaranteed to wipe us out, but they all open doors. If most civilizations hit this stage and mismanage even one of these technologies badly, they might never reach stable, warp-capable maturity. They burn out, collapse, or retreat before they ever start sprinkling probes between the stars. There's also the possibility that those civilizations that do survive choose to be quiet for safety, ethics, or pure disinterest. They might not build galaxy-spanning empires. They might stay local or move into virtual environments, or engineer themselves into something that doesn't care about stars the way we do. From our point of view, looking for loud, wasteful signals, they'd be invisible. Then there's a third option, which is both hopeful and terrifying. Maybe we're early. The universe has not always been equally friendly to life. Early on, there were fewer heavy elements, fewer rocky planets, higher radiation levels, and more violent events. The ingredients for Earth-like worlds and complex chemistry built up slowly as generations of stars lived and died. It might be that only in the last few billion years have conditions become good enough, over enough of the galaxy, for civilizations like ours to appear in large numbers. If that's true, we might be among the first wave, not the only one, but one of the early ones. That would explain the quiet sky. There just hasn't been enough time yet for anyone to spread everywhere, even with fast travel. But it also raises the stakes. If we're early, then what we do in the next few centuries matters a lot, not just for us, but for the future character of the galaxy. Are we going to be a species that turns warp-level control of space-time into a sustainable presence? Or are we going to be one more silent failure, leaving behind nothing but dead artifacts and ambiguous ruins for someone else to find? Either way, the silence is not a comfort. It's a pressure. Because if even one civilization in the history of the Milky Way had cracked warp and stayed stable for, say, 10 million years, this place should look very different to us. The fact that it doesn't means either the universe is hiding deeper rules, or the survival test at this level is brutal. Which leads straight into the most immediate question for you. Standing at the start of this, not the far future but the next few decades, what does the realistic roadmap of warp science actually look like? Not fantasy ships, but specific experiments, simulations, and milestones that tell us whether this is all a dead end or the beginning of a new era. So what does the next 10 years actually look like if warp drive is no longer just a meme, but a research topic? Not starships, not magic, but specific experiments, hardware, and simulations that either push this forward or kill it for good. Start with the vacuum itself, because that's the medium you're trying to hack. Right now, Casimir experiments put two metal plates very close together and measure the tiny force that appears, because certain quantum fluctuations are blocked between them. That force is small but real, and it's direct proof that the vacuum has structure and energy you can slightly tweak. Over the next decade, labs are already planning better versions of these experiments, with new plate geometries, more exotic materials, and ultra-precise force sensors. The goal is simple: map out how much we can really adjust the vacuum energy locally. How big can the negative energy region between plates get before some other effect ruins it? How fast can we switch it on and off? Can we shape it in more complicated ways than just flat plates? None of this is sci-fi, it's nanotech and precision metrology. The more detail we have on what the vacuum will and will not let us do, the tighter the bounds on any warp design that depends on negative energy. At the same time, gravity itself is under a microscope, literally. Physicists already run experiments where they test gravity at sub-millimeter scales, looking for tiny deviations from the inverse square law. They hang small masses from ultra-sensitive torsion balances, or use micro-cantilevers that deflect by absurdly small amounts when exposed to a gravitational pull. If there are extra dimensions, new forces, or small-scale modifications to gravity, those setups might see hints. Warp ideas feed straight into this. Any attempt to shape spacetime in the lab has to be consistent with all these precision tests. If you claim a warp field in a chamber, but a nearby torsion balance doesn't twitch the way the equations say it should, something is off. On the flip side, if one of these experiments sees a consistent anomaly, something that doesn't fit standard, gravity but lines up with a warp-like energy configuration that becomes fuel for new designs, the line between weird gravity result and warp-relevant clue gets thinner. Behind all of this, supercomputers do the heavy lifting. We already use big clusters to simulate black holes merging, neutron stars colliding, and the whole evolution of the universe. Those codes solve Einstein's equations across grids of space-time, tracking how matter and energy move and how curvature responds. The next step is obvious. Point the same machinery at dynamic warp bubbles. You feed different bubble shapes, different energy layouts, different time profiles into the code, and you watch what happens. Does the bubble remain stable? Does it shed energy as gravitational waves? Does it spawn tiny horizons or close time loops? You treat the supercomputer like a warp wind tunnel, running thousands of designs and throwing away the ones that are obviously unstable, inefficient, or causality breaking. What survives that process becomes your short list for real experiments, because building hardware for something the simulator already says will explode is a waste of time and money. While all that is happening on the ground, our detectors in space and on Earth are listening to space-time itself. Gravitational wave observatories like LIGO and Virgo have already picked up signals from merging black holes and neutron stars. Future detectors, especially space-based ones like the planned LISA mission, will be sensitive to slower, longer wavelength ripples in space-time from supermassive black holes. In principle, that same sensitivity could pick up strong artificial distortions if anyone nearby ever builds them. So far, every signal we've caught matches natural sources, but as data sets grow, you can start asking new questions with them. Are there any repeating patterns that look like engineered on-off space-time pulses instead of one-time mergers? Any signals that come from empty regions with no obvious astrophysical source? Even if you don't find anything, those searches give you upper limits, telling you how strong an artificial warp event would have to be before we definitely see it. Flip that around, and you've got constraints on how loud our own experiments are allowed to be if we don't want to announce ourselves loudly across the local neighbourhood. Put all of this together, and you can sketch a rough roadmap that fits in a decade or two, not centuries. First, you get robust, repeatable tabletop experiments that show clear, well-characterized space-time distortions, not just hints. You make devices where turning a field on and off produces a measurable predicted change in light paths or clock rates, and other labs can reproduce it. That's stage one, proving we can poke space-time in controlled ways on small scales. Next, you build larger analog systems that behave more and more like full bubbles. Maybe you use flowing fluids, Bose-Einstein condensates, or metamaterials to create effective metrics that mimic key parts of warp geometry, including how signals propagate in them. These are not starships, but they let you study stability, wave propagation, and possible failure modes in a regime you can film, probe, and reset easily. Finally, if all of that holds up, you aim for tiny test payload surfing micro-warp regions. Not people, not even big hardware, just small masses or light pulses interacting with engineered space-time dents over centimeters or meters. You try to show that relative to a control path, the payload moves as if it had gotten an effective speed boost that can't be explained away by ordinary forces or refractive tricks. That's the point where warp is no longer a word in a paper, but an effect on an object's actual motion, even if it's just by a microscopic amount. Every one of these steps will be noisy, controversial, and surrounded by hype. Early results will be overclaimed, then cut down by replication attempts. Theoretical bounds will be updated again and again as new data comes in. There will be false alarms, warp drive discovered headlines that don't survive a year of scrutiny. But if even a small subset of the effects are real and repeatable, and match warped space-time predictions, then the field moves from internet speculation to a legitimate branch of experimental gravity. And when that happens, you're left with the final uncomfortable layer. If we actually cross the line and sculpt space-time on command, even at small scales, what does that do to your personal future? Your idea of where you can go, what you can see, and what kind of species you're about to become. How far does your life actually reach if you're honest about what physics allows today? Right now, your personal future is basically shackled to one small planet, plus maybe a tiny bubble around it. Low Earth orbit, maybe Mars if things go very well and you're willing to accept a one-way or very long trip. Everything else in the sky is just background, pretty and unreachable. A real warp capability blows that up. Your reachable future suddenly includes other star systems, not as wallpaper, but as places you could physically stand on or send machines to and hear back from within a single human lifetime. Imagine being born on Earth and dying after having visited another star's planets, seeing their skies, their weather, their weird geology, or at least getting real-time or near real-time updates from probes bouncing between multiple systems. The idea of home stretches from one world to a cluster of stars with shared history. The decisions you make about education, industry, energy suddenly have to account for the fact that your kids, or your kids' kids, might actually live under another sun. And that raises a harder question. If you can really move between stars, what does that do to the story of what humans are? Right now, humanity's footprint is small in a way that's almost embarrassing given how loud we talk about progress. A handful of people in low Earth orbit, some robots crawling around Mars and the Moon, a couple of aging probes barely beyond the edge of the planets, limping along decades after launch. That's it. For all our technology, we're still basically a local species, poking the shoreline of a cosmic ocean and then running back inside when it gets cold. Warp-level technology flips that framing. The galaxy stops being a distant backdrop and becomes a map you can actually use. Interstellar shifts from a movie genre to a logistics problem. You start talking about supply chains that span star systems, about common standards for navigation beacons around different suns, about who gets to control the high traffic routes between clusters of habitable worlds. Even if you move slowly, even if it takes generations to build that network, the direction is totally different from where we are now. And that leads to a weird twist. Science itself starts to feel like myth-making in real time. In the past, when people wanted to imagine beings crossing the sky, they had to invent dragons. Today your chariots are built from interferometers, quantum field theories, cosmology data, and brutal engineering. If warp works even at microscopic scales, you're watching humans take the most abstract, unforgiving pieces of physics and turn them into practical tricks. From the outside, to someone who doesn't know the math, that looks like magic. We calculated the vacuum, then told spacetime to bend here and not there, and it listened. But from the inside, you know exactly how much pain went into that trick, how many failed experiments, how many negative results. The myth isn't that we cheated the universe. The myth is that we earned one tiny new move in a game with rules we didn't write. That forces you to ask, once you can do that even once, how do you decide what to do next? Look up at the night sky after that, and it's not just pretty anymore, it's a list. Every deep field image from a space telescope, every catalogue of exoplanets with rough sizes and temperatures, every map of nebula and star-forming regions, all of it changes category. Those aren't just interesting objects for papers, they are potential destinations, resources, neighbours. You'll start sorting them not just by mass and metacity, but by reachable with a first-generation warp drive, reachable with refueling infrastructure, too far unless we get better field efficiencies. Some systems become priority targets because they have multiple potentially habitable planets. Some dusty regions become off-limits because they're radiation traps at warp speeds. Over time, the sky stops being a vague dream and becomes a to-do list. Who gets to go where first? Who decides which worlds are preserved, which are mined, which are settled, which are left as scientific parks? And under all of that sits the real cliffhanger. You have to zoom back in from the sci-fi future to the current reality, which is still a lab bench. The final image isn't a gleaming starship, it's that tiny warp test rig humming on an optical table, lasers tracing invisible paths, sensors dumping incomprehensible graphs onto monitors. Right now we're at the stage of nudging spacetime by amounts so small you need ridiculous instruments to even prove it happened. But psychologically, something huge has already broken. For the first time in history, a serious group of scientists can stand up, show data and say, this tiny effect right here, this is space-time reacting to a pattern we designed. Not an accident, not a distant supernova, or a random black hole we're just watching. A response to a human-built configuration on command in a controlled environment. That doesn't mean starships are guaranteed. Quantum gravity might still slam a door in our face. Engineering might still prove too brutal at large scales. Civilization might trip over its own other problems long before warp is mature. But we've crossed a mental line. The universe is no longer just a set of rules we read from far away. It's something we poke, and it pokes back in ways that match our calculations. So the real question is not can we bend space-time, because we're starting to see that answer in the data. The real question is what we do with that ability without tearing ourselves apart, or turning the sky into just another thing we exploited and ruined. The lab rig doesn't answer that. It just hums along, showing that space-time will listen if we talk to it the right way. The rest of the story, the part about whether we turn into a careful galactic species or a brief loud mistake, that part is on us. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.